So answer to the previous question. So what is the orthogonal of a space that has dimension 1 in the end, okay? That is spanned by one single vector. Okay, so we're looking for x such that, well, x is going to be all the x's elements of R3. So let's say they have x, y, and z as component, such that x with the vector a, b, c is equal to 0. Okay, what defines all these x's? So let's just write this inner product is equal to 0. So that's a times x. So, sorry, a times x plus b times y plus c times z is equal to 0. Do you recognize something? Can you identify anything? Well, probably yes, I hope. That's the equation of a plane, okay? That's the equation of a plane that tells you that it's all the xyz that are orthogonal to some vector. So ABC is actually the normal vector to the plane. Okay, so the Cartesian equation comes really from this idea that we are writing that a plane is going to be the orthogonal complement to this line direction. Okay, good. All right, let's see what comes next. Right, so the next theorem, if F is a finite dimensional linear subspace in E is equal to F plus orthogonal complement of F. Actually, I more or less, that's a very intuitive idea. I more or less already used that kind of thing earlier in my small drawing. Okay, so how can we see that? Okay, so we want to prove that in an inner product space E, if we've got a linear space F, then it makes a direct sum with its orthogonal complements. So this we know it well. We have the intuition it's going to be a direct sum because their intersection has to be equal to 0. That's pretty intuitive. But then this direction makes the whole space E. So let's see what we can do. All right, so let's assume that you've got x in E, okay, and I want to prove that it can be written as an element in as x will be equal to some part that belongs to F plus some part that belongs to F orthogonal, and that this is a unique decomposition. That's again, that's what it means to show that we have a direct sum. Okay, so that's what we need to prove. Let's do an analysis and then say this reasoning. All right, so if x is equal to this thing, if we have solved the problem, how can we describe the xf and the xf orthogonal? All right. Xf belongs to f, all right? So that means, so let's say we are given, let's take some very basic, it's not an assumption, we know we can do that. Let's denote E1 up to, let's say, EP, basis, orthonormal basis of F, okay? All right, so that means that xf will be written as, well, we know how to express an element of a linear space with respect to one of its orthonormal bases. We know that it's going to be the sum of some components, xfi times dei, and we know that these components are given by this inner product. Okay, I equals 1 to p. That's very important to know how to use. Okay, then we know that xf, if x is equal to xf minus f xf orthogonal, we can say that xf orthogonal is just going to be given as, sorry about that, let's go back, as x minus xf. Okay, so what do we get? That belongs to f orthogonal, so we get that xf orthogonal with any EI, of course, is going to be equal to 0. That means that X minus XF with any EI is going to be equal to 0. So what do we get? We get that XFEI, well, you expand that by linearity, is equal to XEI. Okay, so that's quite a nice thing that it tells you that, well, you can find actually the part, if that is true, the part that belongs to F, actually you can find it. You can find it by saying it's just going to be the linear, it's going to have as components the same components as X would have on this basis EI of F. Okay? Next, so that was the analysis. Then let's do the synthesis. Okay, so synthesis. Okay, so we said synthesis. So now we take X, any X in E, and we are going to define, we put XF is equal to the sum, okay, from 1, I is equal to 1 to P of scalar product of that X in E with all the elements of the basis of F. Of course, as it's linear combination, it's going to be elements in F, all right? So that's fine. And I put XF orthogonal is equal to X minus XF. Okay, so what I said is that trivially that belongs to F because it's just a linear combination of elements of F, and for any element X in E, of course I can define that. I'm just using the scalar product of X with the elements of the basis EI, right? So that belongs to F, and that's what we need to show, is that if this is the way we define, and then it's going to be uniquely defined. If that's the way we define the second part, we need to show that this belongs to F orthogonal. Okay, so this is not proven yet, so that's what we need to prove. So how to show that it belongs to F orthogonal? We saw one previous theorem. We just need to show that it's orthogonal to any of its bases. So let's take that basis EI. So let's take X minus XF scalar product with any of the EI element of the basis. Okay, so EI. So what is that? That's X EI minus XF EI. Okay. How did we define the XF EI? That's X EI minus, so XF was the sum of, let me take another index so that we don't get mistaken. J is equal to 1 to P of X EJ, EJ with respect to EJ. EI, sorry, that's really the ice. This one is correctly, let me erase that if I can. Okay, so that was really the I here. Okay, so now if I expand this by linearity, so that's minus the sum, J is equal to 1 to P. The scalar product inside here, this one, that's a real number, so I can put it out by linearity, that's XEJ, and then I've got EJ, EI. Okay, but as this is supposed to be an orthonormal basis, that is going to be equal to, so that's, sorry, that's equal to 0 if I is different from J. Okay, so in the end, what do we get? We get that this is equal to XEI minus well, it's going to select only the one where in that sum it's going to select only the only non-zero term of that sum is going to be the one where j is equal to I. So x ej sorry ei times ei ei. Then as this is an orthonormal basis, again that's actually the norm of ei square, which is equal to 1. So that's equal to 0. So what have we proved? We have proved that x minus xf scalar product with ei, any ei of the basis, is equal to 0. So x minus xf belong to f orthogonal. And then we really have this direct sum. Okay, so that is pretty intuitive. Okay, it really tells you that, well, you can visualize your linear space. Let's say it's something like a plane or whatever, it's a linear space, and you've got a subspace. Well, it's just a subset of E, and then its complement is what's outside of it, actually. Okay, and the whole thing together, they make E. Or if you, another example, a visual example, maybe more rigorous than this previous one, is in R2. Okay, take in R2, all right? Take any direction, okay? If I want to take a strict subset of R2, it's just going to be the spanning space of, well, you need the 0 of R2 to belong to that direction, and it's going to be spanned by some vector u, okay? So, of course, the orthogonal complement, if you use the usual scalar product, it's just going to be what you expect, okay? That would be so let's say that this is f, that would be f orthogonal, okay? And the sum of those two linear space is going to make R2 together. Why? Because simply because any x in R2, you can express it as one part, uniquely as one part that belongs to f, and one part that belongs to its orthogonal. Okay, or in R3, some kind of stuff, you've got a plane of dimension 2. Sorry. So you've got a plane of dimension 2. So this one, so it has those two directions, and we already saw that its orthogonal would be the normal vector to that plane. Okay, and so again, the idea is very similar, is that then you come to express any x in R3 very simply as one part that belongs to the space and one part that belongs to its orthogonal complement. Okay, so this is a very intuitive idea. We sort of already dealt with that when we were talking about direct sums, but here we get things straight. Okay, using the orthogonality concepts that we have now clearly defined.